Well, let me tell you something that happened on September 14th, 2015 at 5:51 in the morning, Eastern Time. Two detectors, one in Louisiana and one in Washington State, 3,000 kilometers apart, heard something, a chirp, a vibration in space itself. It lasted a fifth of a second, and in that fifth of a second, everything changed, because what those detectors heard was the sound of two black holes colliding 1.3 billion years ago. The ripples from that collision traveled across the universe for longer than complex life has existed on Earth, and when they finally reached us, they stretched space by less than 1/10,000, the width of a proton. Think about that. We built a machine sensitive enough to measure something that small. And we did it because a man sitting at his desk in 1916 predicted it would happen. Now, let me tell you what gravitational waves actually are, because you probably have some picture in your head, and it is probably not quite right. Einstein's general relativity says that massive objects warp space-time. You've probably seen the demonstrations, the rubber sheet with a bowling ball making a dip, and smaller objects rolling around it. That's not a bad picture, but it misses something important. Space is not just bent like a surface. Space itself, the fabric of reality, gets curved by mass. And when massive objects accelerate, when they orbit each other or collide or explode, they create ripples in that fabric, ripples that travel outward at the speed of light, stretching and squeezing space as they pass. Everything in the universe that has mass and accelerates makes gravitational waves. You make gravitational waves when you wave your hand. The Earth makes gravitational waves as it orbits the Sun, but the effect is unimaginably small. Even the most violent cosmic events, black holes colliding, neutron stars spiraling together, massive stars exploding, produce waves that, by the time they reach Earth, have stretched space by a fraction of the width of a proton. Einstein himself knew this. In 1916, just months after he published general relativity, he worked out that the theory predicted gravitational waves. And then he calculated how small the effect would be. And he said essentially, well, that's interesting, but we will never measure them. Never. The technology required would be impossible. For decades after, many physicists thought gravitational waves might not even be real. Maybe they were just mathematical artifacts, curiosities of the equations with no physical meaning. You see, general relativity is a very complicated theory. The math is beautiful, but interpreting it is hard. And when you have something predicted by equations that seems impossible to ever measure, you start to wonder if it is really there. But here is what happened. In the 1970s, two astronomers at the University of Massachusetts Amherst, Russell Hulse and Joseph Taylor, were doing something that sounds pretty routine. They were observing pulsars. Pulsars are neutron stars, the collapsed cores of massive stars, spinning incredibly fast and shooting out beams of radio waves like cosmic lighthouses. And Holtz and Taylor found one called PSR B 1913 plus 16. Very brilliant discovery. But this pulsar was special. It was orbiting another neutron star. Now, this opened up something wonderful. If gravitational waves are real, if they actually carry energy away from massive accelerating objects, then this binary pulsar should be losing energy. The two neutron stars should be spiraling closer together, very slowly. The orbit should shrink. And you could measure it. You could watch the pulsar's timing, watch how its radio pulses arrive at Earth, and if the orbit is shrinking, the timing would change in a very specific way. So they watched. For years. They measured the pulsar's orbit with incredible precision. And you know what? The orbit was shrinking. Exactly, and I mean exactly, at the rate predicted if gravitational waves were carrying energy away. The match was perfect, down to a fraction of a percent. In 1993, Hulse and Taylor won the Nobel Prize for this indirect confirmation of gravitational waves. But nobody had actually felt the gravitational wave pass through. Nobody had directly detected one. And that is a very different thing. Indirect evidence is wonderful, but physics is about measurement. You want to put a detector out there and say, there, I felt it, I measured it, here is the signal. And this is where the story gets very interesting. Because building a detector sensitive enough to measure a gravitational wave is one of the hardest things humans have ever attempted. The idea started in the 1970s and 80s with three physicists, Rainer Weiss at MIT, Kip Thorne at Caltech, and Ronald Drever from Glasgow. They proposed building something called the Laser Interferometer Gravitational Wave Observatory, LIGO. The design is conceptually simple but practically insane. You build two L-shaped detectors. Each arm of the L is 4 kilometers long. You put mirrors at the ends. You shine a laser beam down each arm, bounce it back and forth between the mirrors hundreds of times, and then recombine the beams. If a gravitational wave passes through, it stretches space in one direction and squeezes it in the other. The arm lengths change. The laser beams go out of sync. You detect the difference. How much of a difference are you looking for? Remember, even a violent cosmic event produces waves that stretch space by less than 1/10,000th the width of a proton. A proton is already unimaginably small. You are trying to measure something smaller than that, over a distance of 4 kilometers. Think about what that means. If you scale the Earth up to 4 kilometers, you would be trying to measure a change smaller than an atom. And you have to isolate this measurement from every possible vibration. Traffic on a nearby highway? That is a problem. Earthquakes on the other side of the world? That is a problem. Ocean waves crashing on a beach 100 kilometers away? That is a problem. Someone walking past the building? That is a problem. The mirrors are suspended on incredibly complex isolation systems, layers and layers of damping to filter out all of this noise. And even then, you are looking for a signal buried in noise. They built LIGO, two detectors, one in Livingston, Louisiana, one in Hanford, Washington State, 3,000 kilometers apart. Why two? Because if you detect something in just one detector, you do not know if it is real or just noise. But if you detect the same signal in both detectors, separated by thousands of kilometers within a few milliseconds of each other, then you know it is real. It came from space. LIGO started taking data in 2002, and they found nothing. Years of nothing. They upgraded the detectors. More years of nothing. The sensitivity was not quite there. Gravitational waves are so weak that even with 4-kilometer arms and lasers and isolation systems, you are right at the edge of what is possible. So they upgraded again. Advanced LIGO. Better lasers, better mirrors, better isolation. The sensitivity increased by a factor of 10. Now, if gravitational waves were out there at the predicted rate, advanced LIGO should see them. Should. But nobody knew for sure. Maybe the universe was quieter than expected. Maybe black hole mergers were rarer. Maybe there was some reason it still would not work. Advanced LIGO came online in September 2015. Not fully online, just engineering runs, testing the systems, making sure everything worked. Not yet in official science mode. September 14, 2015, 5:51 in the morning, Eastern Time. Both detectors register a signal, Livingston first, then Hanford 7 milliseconds later, exactly the light travel time between them. A chirp, the frequency rising from 35 Hz to 250 Hz in a fifth of a second, then silence. The scientists thought it was a test signal at first. They had been injecting fake signals into the data to test their analysis pipelines, to make sure they could detect things when they were there. Someone must have injected a test without telling everyone. But no, it was not a test, it was real. The waveform matched perfectly with computer simulations of two black holes spiraling into each other. Not just roughly, perfectly. You see, physicists had been running simulations for years, solving Einstein's equations on supercomputers, figuring out what the gravitational wave signal from different types of collisions would look like. And this signal matched those simulations so precisely that they could tell you exactly what happened. Two black holes, 36 and 29 times the mass of the Sun, orbiting each other. They had been orbiting for millions of years, slowly losing energy to gravitational waves, spiraling closer and closer together. In the final second, as they approached the speed of light, the gravitational wave emission became intense. That final second is what LIGO heard, the chirp. The frequency rising as they spun faster and faster, closer and closer, and then the merger. They became a single black hole of 62 solar masses. Now, here is something remarkable. 36 plus 29 is 65. The final black hole was 62 solar masses, 3 solar masses missing. Where did they go? They were converted to pure energy, radiated as gravitational waves. In that final fraction of a second, the collision released more power than all the stars in the observable universe combined. For that brief moment, the most luminous thing in the universe was not a star or a galaxy or a quasar. It was two black holes merging, and the signal traveled for 1.3 billion years to reach Earth. It left that collision when life on Earth was mostly single-celled. It traveled through space, stretching and squeezing space-time as it went, getting weaker and weaker. By the time it reached us, it stretched the 4-kilometer arms of LIGO by about 1,000th the diameter of a proton. And we measured it. Think about that. We heard two black holes collide. Black holes do not emit light. You cannot see them with telescopes, but we heard them with gravitational waves. The scientists spent months checking. They analyzed the data forwards and backwards. They looked for every possible source of error, every possible way this could be. Noise or a glitch or a mistake. They found nothing. It was real. On February 11, 2016, they announced it to the world. 100 years after Einstein predicted gravitational waves, 99 years after he said we would never detect them, we detected them. The physics world changed that day. Weiss Thorne and Barry Barish, who led the LIGO collaboration, won the Nobel Prize in Physics in 2017. Now let me tell you what has happened since, because this is not just one discovery. This is a new way to observe the universe. As of 2025, LIGO and other gravitational wave detectors have detected over 300 gravitational wave events. 300. Black hole mergers, neutron star mergers, maybe some things we are not entirely sure about yet. Each detection teaches us something. We are learning how often black holes merge, what masses they have, how they formed. We are testing general relativity in the strongest gravitational fields that exist, right at the edge of black holes, where space-time is curved so intensely that the math barely works. And general relativity keeps passing every test. In August 2017, LIGO detected something different. Two neutron stars colliding. Neutron stars are not black holes. They have surfaces. They emit light. And this collision was close enough that telescopes could see it. For the first time, we observed the same cosmic event with both gravitational waves and light. Multi-messenger astronomy. What we saw was extraordinary. The collision produced a kilonova, a massive explosion that created vast amounts of gold and platinum and other heavy elements. We had theorized for decades that heavy elements were made in neutron star collisions, but this was the first time we actually watched it happen. We saw the gravitational waves as the stars spiraled together, then the light from the explosion, then the afterglow as the debris expanded. One event observed in gravitational waves, visible light, X-rays, gamma rays, radio waves, every kind of observation we can make, all pointing at the same thing, all telling us different parts of the story. And there is something else, a gravitational wave background. Just like there is a cosmic microwave background from the Big Bang, there is a gravitational wave background from all the mergers and collisions happening across the universe all the time. Individually, these are too faint to detect, but added together, they create a hum, a constant gravitational wave signal permeating space. We are starting to detect this. Pulsar timing arrays, networks of pulsars across the galaxy whose timing we monitor, are seeing evidence of this background. It is like listening to the universe's heartbeat. Now, you might wonder what this all means. Why does it matter that we can detect gravitational waves? What does this give us that we did not have before? Well, here is the thing. For all of human history, everything we knew about the universe came from light. We looked up at the sky, we saw stars, we built telescopes, we detected radio waves and X-rays and gamma rays, but it was all light. all electromagnetic radiation. And light is wonderful, but it has limitations. Light is emitted by matter. If there is no light being emitted, you cannot see it. Black holes do not emit light. The moments before neutron stars collide, when they are spiraling together at nearly the speed of light, barely emit light. And light can be blocked. Dust clouds block light. The center of galaxies is often obscured by dust. Gravitational waves are different. They are ripples in space-time itself. Nothing blocks them. They pass through matter like it is not even there. And they are generated by the motion of massive objects, not by the emission of light. This means we can observe things that are completely invisible to telescopes. We can watch black holes. We can see neutron stars collide before they emit light. We can peer into the dusty centers of galaxies. And maybe, one day, we can detect gravitational waves from the Big Bang itself. The cosmic microwave background, the light left over from the Big Bang, was emitted 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. But gravitational waves from the Big Bang would have been emitted much earlier, maybe a tiny fraction of a second after the beginning. If we could detect those, we would be seeing further back in time than we ever thought possible. We would be seeing the universe in its infancy, when it was unimaginably hot and dense and strange. We have not detected primordial gravitational waves yet. The signal is incredibly weak, but people are looking. And if we find them, it would be one of the greatest discoveries in the history of science. You know, this is how physics is. You start with an idea, a theory, equations on paper. Einstein, sitting at his desk, working through tensor calculus, figuring out how mass curves space-time. He publishes the theory. It predicts something strange, gravitational waves. He calculates the effect and says, well, that is interesting, but we will never measure it. And for 100 years, most people agree. It seems impossible. But some people do not accept impossible. They say, let us try anyway. Let us build the most sensitive instrument ever conceived. Let us measure something smaller than a proton over a distance of 4 kilometers. Let us isolate it from every vibration on Earth. Let us spend decades building it, upgrading it, testing it. And then, one September morning, it works. The universe sends us a signal. Two black holes colliding a billion light years away, and we hear it. We hear the universe. Einstein gave us the theory. A century of engineering made it real. Hundreds of scientists, thousands of person-years of work, billions of dollars, all to detect something Einstein thought we would never detect. And now we have opened a new sense. For all of human history, we could see the universe. Now we can hear it. We can listen to the collisions of the most massive objects that exist, black holes crashing together in the distant cosmos. We can hear neutron stars spiraling to their doom. We can hear the universe itself vibrating with the echoes of countless mergers across billions of years. And that, I think, is beautiful. That is what science is. You look at the universe and you say, I want to understand this. I want to know how it works. I want to see what has never been seen, hear what has never been heard. And you do not accept that something is impossible just because it seems impossible. You try anyway. You build the instruments, you make the measurements, you test the theory. And sometimes, if you are very lucky and very persistent, the universe gives you an answer. There is still so much we do not know. We do not know what happens at the very center of a black hole. We do not know if we will ever detect primordial gravitational waves. We do not know what other sources of gravitational waves are out there waiting to be discovered. Nobody knows. But we keep looking. That is science. And here we are, biological creatures evolved on a small planet orbiting an ordinary star in an ordinary galaxy, and we have figured out how to listen to the universe itself. We have heard black holes collide. We have measured ripples in space-time so small that they should not be measurable. We have confirmed a prediction made 100 years ago by a man who thought it would never be confirmed. Think about that.